Hello everyone, I hope you are having a good day. This is our video lecture for the lesson on functions. A real valued function f is defined on a set D of real numbers. It is a rule that assigns to each number x in D exactly one real number, which we will denote as f of x. So basically, it is a pairing of a number x coming from a set which we call D, and then we pair that x to a number which we call f of x. The set D of all numbers for which f of x is defined is called the domain of the function f. And the number f of x is called the value of f at the number x. Now the set of all values y equal to f of x is called the range of f. That is, the range of f is the set y such that y is equal to f of x for some x in D. However, for this lesson, we would only be focusing on the domain. So let's say we have the function f of x is equal to x squared. So in this function, we will be taking numbers x and then we will be squaring those. So x, the set of all numbers x will be the domain, and then when you square those numbers are the range. So again, what we want to do here is to determine what is the domain. So the domain here is simply the set of all numbers that we can use for x. Or if we would ask it the other way, is there any number which we cannot use for x? Or is there any real number that we cannot use for x? And the answer is none. Basically, we can use all of the numbers as all of the real numbers as x. So because we are able to use all of the real numbers, then our domain here is the set of all real numbers, R. In your mathematics in the modern world, you have discussed this. You might have written the set notation, so you can write there x such that x is an element of R. We also have what we call the interval notation. So for interval notation, we say that this is from negative infinity up to positive infinity. So any of these three here can be used to write the domain because these three all mean the same thing. These are all equal. Now what if we have the function 2x squared minus 3x plus 1? So for the domain, we would again ask ourselves, is there any number that we cannot use to substitute for x? And then again, there is no restriction. We can put here 0, we can put here 1, we can put 10, 100, negative 3000, negative 400. We can use fractions. We can even use irrational numbers. We can use here pi. We can use here e. So basically, again, there's no restriction. So our domain is the set of all real numbers. So far what we have seen are those whose domain are the set of all real numbers. So let us now look into those whose domain would have exceptions. To go into that, we have to discuss first the concept of division by zero. So when we divide A divide by B, we say that it is equal to a number C if and only if A is equal to the product B times C. So for example, if you have 10 divided by 2, we say that this is equal to 5 because we see that 10 is equal to 5 times 2. So let's now look at numbers involving 0. So first let us have 0 divided by a number, let's say 2. And this is of course 0 divided by 2. Of course we know that this is a 0. And this can be seen because we can express a 0, this one in the numerator, is equal to 0 times 2. Now, how about if the denominator is 0? So let's have 3 divided by 0. What is this equal to? Is this equal to 0? So let's check. Can we express 3 as the product of 0 times 0? It is not. So therefore 0 is not the answer. Is it 3? Is this equal to 3? So this one here, we determined that this is incorrect. So let's have 3 divided by 0. Is this equal to 3? Can we express 3 as the product of 3 times 0? Again, that is incorrect. And for that matter, there is no number here that would suffice the equation. 3 cannot be expressed as the product of any number times 0. So in this case, we say that this is undefined. That means any number except 0 when we divide it by 0 is undefined. Now why do I say except 0? So what if our numerator is actually 0? So 0 divided by 0. Can this be equal to 0? Let's check. 0, is it the product of 0 times 0? Yes, that is correct. But is it only 0 that would suffice? The answer here, can it be 0? Only, let's check. Can I write there 1? So I can write 0 as 1 times 0. So this is also correct. That means actually that any number that I put here would be correct. So 0 divided by 0 is any number because 0 can be expressed as the product of any number times 0. So in this case, there are many answers that we can get when dividing by 0 by 0. So in this case, we say that 0 divided by 0 is indeterminate, meaning it can be any number. So the difference, undefined, meaning there is no number that would suffice. Indeterminate means that any number would suffice. So basically here, going back to the concept of the domains, we can do division as long as it is not division by 0. So let's move on to the next example of a function. Let's say now our function is f of x equal to 3 over x. So again, what we don't want here to happen is that for our denominator to become 0. So it will become 0 if x is equal to 0. So our domain, we can write it as the set of all real numbers except 0. Please take note R, the set of all real numbers, this is a set. So if we are going to take an exception, it must also be a set. So this is a set minus a set. This one here would be incorrect. R minus 0 because this is not a set. You cannot subtract an element and a set. So what we do is a set minus a set. Or we can also write this set builder notation. We can have x such that x is not equal to 0. That's one way of writing. In interval notation, we can have from negative infinity up to 0, open because that means not including 0, union with 0 to positive infinity. So this means that we can go to any number that's very close to 0 but not equal to 0. We would illustrate this more later when we do graphing. Let's have another example here. Let's say our function now is this rational expression 3x plus 5 all over 2x minus 4. So again, what we don't want here is for 2x minus 4 to be equal to 0. So what value of x will make it 0? So what we simply do here is solve this equation. So what we're doing is setting the denominator to be equal to 0. So we solve to x is equal to positive 4. So x is equal to 2. So our domain this time is the set of all real numbers except the number 2. Or in set builder notation, x such that x is not equal to 2, or in the interval notation from negative infinity up to 2 union with 2 up to positive infinity. Okay, this time what we have is a function that is called piecewise function. Piecewise, basically we are taking the function piece by piece. This is often done so that we can have the domain as the set of our real numbers, because if there are numbers which would make the function undefined, those numbers are given a different definition. So in here, what we have here, the function h of x, if your x is greater than or equal to 0, then we will use the function x squared. But if your x is less than 0, meaning if it's negative, we will be using the function square root of negative x. If you notice here, if it's a square root would become undefined if the base here is negative. So by making x here negative, so negative times negative, this will become positive, so the square root would still be defined. Now, we have, if you remember in the definition, we have what we call the values of x. So we can look for, we can assign values of x, and then what is the value of h of x. So if our x is equal to, let's say 2, then we will be using the h of x, our h of 2 will be equal to 2 squared, because it's greater than 0, so we use x squared, so this is equal to 4. If we have 1, then h of 1 is equal to 1 squared, so this is equal to 1. If we have 0, so 0, that would fall into this definition, x greater than or equal to 0. So we use h of 0 would be 0 squared, which is again 0. But if we now have, let's say, negative 1, so our h of negative 1 is square root of the negative of negative 1. So this is square root of 1, and that is 1. And if we have, I'm just going to use a perfect square, so I'm going to use negative 4. So h of negative 4, again, because this is less than 0 now, so this is square root of the negative of negative 4. So this is square root of 4, so this is equal to 2. So on a piecewise function, when you are going to evaluate, always look at the definition. Where does it fall? Will it fall on the first definition or the second definition? We also have piecewise functions which would have 3 definitions. So on those cases, you would have to look closely where your x falls. Is it on the greater than or equal to 0 part, less than 0 part? Sometimes, again, if you say, if we have 3 definitions, it can also be like greater than 1 or less than 2. So things like those. The definition here would change. So now let us go to the graph of a function. So a graph of a function, f is the graph of the equation y is equal to f of x. So basically here we will be plotting points, pairing points x and f of x. So f of x will be assigned as our y. You should have had this in your analytic geometry. And then we will just plot them in the Cartesian plane. So one of the easiest ways to do this is to do the point plotting method. So we will be choosing certain values of x Most common would be these values from -2 to +2, which is the integers, and then substitute them into the f of x, into your function. So we have already, I already put the values here. So if it's -2, then f of x is -1, or f of -2 is -1. F of -1 is +2, f of 0 is +5, f of 1 is 8, and f of 2 is 11. So we draw our Cartesian plane here. This is not, of course, perfect, but this is just a guide on how to do this. So we put here 1, or let me change this, make it a bit bigger. It's really hard to draw using the pen tab. Okay, so we have here and here. So let's put here our 1. Here's our 2. Here's our -1, and here's our -2. So this one here, of course, is 0. This one is 1, 2, 3, and so on. So if our x is -2, we put here -1. Our f of x is -1. Let me change the color. So it's this. If our x is -1, it's +2. If it's 0, it is +5. So somewhere there, and +1. And then we just connect those points. Again, pen tab is really hard to do. So something like that. As long as the points are connected. So later on, I will be showing you something that would make life easier when we do graphing. Let's first get to another example. Let's say our function now is equal to x squared minus 2x plus 1. So I again did some point plotting already here. So we have f of -2 is +9, f of -1 is 4, f of 0 is 1, f of 1 is 0, f of 2 is 1. By the way, let's go back to this equation. F of x equal to 3x plus 5. If you will notice, this is what we call a linear equation, or a linear function. So linear function because the graph here is a line. This one here is a quadratic function. For quadratic functions, we can always expect our graph to be that of a parabola. So we now have we have those points. We will draw our Cartesian plane. So let's say we have this. Then we will have again -2, -1. That's a 0 there. That's 1, and then that's 2. Our numbers can go up to 9. So let's make it a bit small. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if it's -2, it is +9. So we change again the color. So it should be somewhere here. If it's -1, it's +4. So here. If it's 0, it's +1. If it's +1, it's 0, and +2 is 1. So we connect these dots and make sure that the graph is that of a parabola. Again, you would be having a hard time. I'm having a hard time doing this on a pen tab, but there is a helper for us. I want you to be able to discover this site, desmos.com/calculator. So in desmos.com, in the Desmos calculator, you can enter your equation here. So do not write anymore the f of x. Simply write the x part. So it's x squared minus 2x plus 1. I want you to discover how to write the exponent. Discover it for yourself. And when you hit enter, it would automatically draw your graph. Okay, this one here, just to note that this one here, this will just be a guide for you on if to check if your graph is correct. I still want you to be able to make the graph on your own on your graphing paper. Let's go back to another example. So let's now say we have this graph f of x is equal to 3 over x. So as it was shown earlier, our domain is the set of all real numbers except 0. So we have here 0 is put as undefined. And then we have here f of negative 2 is negative 1.5, f of negative 1 is negative 3, f of 1 is 3, f of 2 is positive 1.5. This should be sort of easy for some if you already know the concept of asymptotes. So I'm making here the rotations. So we go up to 3, 1, 2, 3, so 4, here negative 1, negative 2, negative 3, and negative 4. Okay, so what we have here is we have, if it's negative 2, it's negative 1.5. So negative 2, negative 1.5 is between negative 1 and negative 2. If it's negative 1, it's negative 3. If it's positive 1, it's positive 3, and positive 2, it's 1.5. Okay, this doesn't really tell us what would happen with our graph. You might be tempted to just connect the dots here, but that's not how it should happen. Okay, so what would happen here? It would be better if we would look closely on what is happening between negative 1 and before it becomes 0. So the f value is from negative 3 here. What happens from this negative 3 up to where does the graph go? So it would be better if we have this. So we will be going from negative 1. What would happen if our value is at negative 0.75, negative zero point 0.5, negative zero point 0.1, negative 0.01? So what are the corresponding f of x's for these numbers? If our x is negative 0.75, then our f of x is negative 4. So it is somewhere here. Here. If our x is negative 0.5, our f of x is negative 6, so probably somewhere here. If it's negative zero point 0.1, it's negative 30, so that's way below there. So what's actually happening here? Our graph keeps on going that way. With the positives here, it's also the same. It's mirrored. It's just that it's going to the positive. The values are positive, so it's going up there. Okay. So again, if to make sure that we have the correct graph, let's go to Desmos. So if you just write in here the next equation, it would overlap. So it's better if we erase this one by clicking on the x, and then we write 3 over x. Okay, this is a bit big, so let's zoom out. Okay, so this is the graph of 3 over x, or the function 3 over x. So if we zoom in here, so remember what I said, between 1 and 0, or between negative 1 and 0, so these are the values here. So let's zoom in some more. So there you have it. So here we have the value negative zero point 0.5, and we got here 6. At negative zero point 0.5, our x is 6. And then we have many other possible values. Okay, so that would be all for our lesson for functions. So what we did is to determine the domain, and we also did some tabulation, getting the values of our function at certain values of x, and we also did some graphing of the functions. So expect that that's what you would also be doing in your problem set. That will be all for today. Have a good day. Keep safe.